Okay, hey guys. So in the last tutorial, we put up a triangle and then we turned it into a rectangle and then we turned on wireframes and did some other cool stuff. This time, this next one is more about shaders, and we're going to just learn a bit more about them, what they're for, and what other cool stuff we can do with them. So this one's not too long. I actually did it yesterday. Oh yeah, because of that, I need to revert back to the previous state. Yeah, so what I'm gonna do is I've got a GitHub. What's this? I've got a GitHub. Just get rid of this. I've got a GitHub repository. There's a link to it, and you can check out this one, cleanup after day 2 Hello Triangle. And if you do that, you can continue along with me on the stream and do this tutorial. So this basically takes you to the start of this section, shaders. All right, so let's open it up. So if we go here into create window, we should still be on the triangle section. Yeah, it looks like we are. And it's actually going to draw a rectangle. Yeah, so that's where we were at the end of yesterday's stream. So let's just read a bit of this. I don't think it's too lengthy. As mentioned in Hello Triangle, shaders are little programs that rest on the GPU. These programs are run for each specific section of the graphics pipeline. In a basic sense, shaders are nothing more than programs transforming inputs to outputs. Shaders are also very isolated programs in that they're not allowed to communicate with each other. The only communication that they have is via their inputs and outputs. The reason they're so isolated is because they're designed to be highly parallelizable. That means potentially you could have 1,000 of these shader programs running at the same time, and they're not supposed to have any side effects, right? So if you want to, I don't know if you guys have, but if you want to make code highly parallelizable, you basically kind of limit the variables it can affect, and make sure that it doesn't depend on stuff that, yeah, it's just all about making it parallelizable. Shaders are written in a C-like language, GLSL. GLSL which is basically OpenGL shader language, is tailored for use with graphics and contains useful features specifically targeted at vector and matrix manipulation. Shaders always begin with version declaration. That's here. Version, followed by a list of input and output variables, uniforms, and its main function. Each shader's entry point is at its main function, where we can process any input variables and output the results in its output variables. Don't worry if you don't know what uniforms are, we'll get to those shortly. A shader typically has the following structure. So version number, input variables, output variables, a uniform variable, and the main program. It does some code. Out variable names equals weird stuff we process, right? When we're talking specifically about the vertex shader, each input variable is known as a vertex attribute. There's a maximum number of vertex attributes we're allowed to declare, limited by the hardware. OpenGL guarantees that there are always at least 16 4-component vertex attributes available, but some hardware might allow for more, which you can retrieve by querying gl_max_vertex attributes. I mean, we can do this. This is like just a little. It's just about seeing what's the max number of vertex attributes we can set. So let's just do it just to see. GL in nr attributes. GL get integer iv. Is that it? Integer v. I think integer v is integer vector value, maybe. GL_max attributes. Max attrib. Max vertex attrib. And then reference to that in our attributes. And then let's printf instead of std, because I'm like that. Max GL max vertex attributes. And our attributes equals %I and our attributes, right? And then if we run, we should get this value. So it's also 16, which is kind of a bummer because I was thinking my graphics card was so beefy that it would like allow for more, but no, it doesn't. Oh, I hate that. Why does it do that? I wish it would like. Why does it sometimes come out as a block and sometimes it comes out like that? I see. Okay. Anyway, actually we don't need this at all, so I'll just kill it. It's just a little query. Oh, somebody's here. Why do you use printf in C++? I like the syntax better, that's all. I mean, it's a bit neater. It's just a personal thing. You don't have to. You can use std out if you like. Oops. That's really annoying. That's really annoying. Alright. GLSL has, like any other programming language, data types for specifying what kind of variable we want to work with. GLSL has most of the default basic types we know from languages like C, int, float, double, blah, blah, blah. GLSL also features two container types that we're using a lot throughout tutorials, namely vectors and matrices. This is pretty cool. A vector GLSL is a 1, 2, 3, or 4 component container for any basic types just mentioned. You can take the following form. So you can have a vector for vector n is the default vector as floats. Vec n is booleans, integers, unsigned integers, doubles. So it's just, yeah, there's lots of vectors you can define. You can define a vector in booleans if you want. It's kind of cool. Most of the time we'll be using the basic vec n since floats are sufficient. Components of a vector can be accessed via vec x, y, z, w. GLSL also allows you to use RGBA for colors or STPQ for texture coordinates. Yeah, so you can just so if you have a vector, you can use x, y, z, or you can use RGBA, or you can use STPQ if you want, and they all mean the same things respectively. It's just about, you might use RGBA if you have a color, and you might use STPQ if you're doing texture coordinates. It's just a way of documenting your code a bit better. The vector data type allows for interesting and vector and flexible component selection called swizzling. Swizzling allows for the following syntax: some vec, different vect, x, y, xn. So that's cool. It's basically like this vector might be like 1, 2, 3, 4, and then this different vector is set to the x, y, and xx components. So this vector will be like 1, 2, 1, 1, right? And then this vector, oh well, I don't want to try and figure out this stuff. But basically, the syntax is really cool. It's pretty flexible as well. It just lets you like create and add and access vectors in a nice way, so that you write it as code, right? Or cleaner code. You can use any combination of up to 4 letters to create a new vector of the same type, as long as the original vector has those components. It is not allowed to act as the z component of a vector 2, for example. Yeah, that makes sense. We can also pass vectors as arguments to different vector constructor calls, reducing the number of arguments required. Yeah, so this guy defines vector 2, and then he passes the vector 2 into a vector 4 constructor, and then that's just assumed to be the x and y, and then this is z and w. Same sort of thing here, x, y, z, and then this is w. It's just syntax stuff. Shaders are nice little programs on their own, but they are part of a whole, and for that reason we want to have inputs and outputs in the individual shaders so that we can move stuff around. GLSL define the in and out keywords specifically for that purpose. Each shader can specify inputs and outputs using those keywords, and wherever an output variable matches an input variable, the next shader stage there passed along. The vertex and fragment shader differ a bit though. The vertex shader should receive some form of input, otherwise it would be pretty ineffective. The vertex shader differs in its input in that it receives its input straight from the vertex data. To define how the vertex data is organized, we specify an input variable with location metadata so that we can figure out the vertex attributes on the CPU. We've seen this in the previous tutorial as layout equals layout and then location equals 0. The vertex shader thus requires an extra layout specification for its input so that we can link with the vertex data. It is also possible to omit the layout location equals 0 specifier and query for the attribute locations in your OpenGL code. But I prefer to set them in the vertex shader. It's easier to understand and saves you and OpenGL some work. The other exception is that fragment shader requires a vec4 color output variable. Since the fragment shader needs to generate a final output color, if you fail to specify an output color in the fragment shader, OpenGL will render your object black or white. So if you want to send data from one shader to the other, we'd have to declare an output in the sending shader and a similar input in the receiving shader. When these types in the name are equal on both sides, OpenGL will link those variables together, and then it is possible to send data between shaders. This is done when linking a program object. To show you how this works in practice, we're going to alter the shaders from a previous tutorial to let the vertex shader decide the color for the fragment shader. So here, this is the vertex shader, and the output variable is vertex color, right? So in the main, we just set that to some color, I think dark red. And then the input for the fragment shader is vertex color, the same one that's out from here. So vertex shader comes before fragment shader. Vertex shader shoots out a vertex color. Fragment shader wants a vertex color. And so the OpenGL linking stage is smart enough to think, okay, these two link, so this goes in here, and then when we set it in here, the color is there, and then we want the output of this, right? So let's see if that works. Let's actually try that. You can see we declared a vertex color. Yeah, I think it's just explaining what I said, so let's just do it. So up here we still got our vertex shader and our fragment shader, like written in line in our CPP source code. We're gonna fix that later, but for now we'll just continue working in this weird way. So the vertex shader needs an output. Yeah. Out vec4 vertex color. Bam, bam, bam. Oh, we don't need the comment. Don't need that either. And then vertex color, we're gonna set it after GL position. Just add that in. I think that's good. Yep. And then the fragment shader will define an input variable and then assign the input variable, right? That's it. I think it makes sense to have input variables before output variables in vec4 vertex color. Oh, there is this. Yep. And instead of defining it there, we'll just use vertex color. And I think that's it. So that should work, right? Yeah, I mean, the reason we get a square instead of a triangle is because we, yeah, it's because we've got a square defined here, or a rectangle. Let's just stick with the rectangle. I could change it, but it's a bit trivial. It's basically just changing these positions and changing the indices. You just work here. Okay. Uniforms. Uniforms are another way to pass data from our application to the CPU on the CPU to shaders on the GPU. But uniforms are slightly different compared to vertex attributes. First of all, uniforms are global. Global meaning that a uniform variable is unique per shader program object and can be accessed from any shader at any stage in the shader program. Second, whatever you set the uniform value to, uniforms will keep the values until you either reset or update. Yeah, so uniform variables are global and they're read-only by the shaders. The shaders can't adjust them. OpenGL side can adjust the uniform variables. So that's why can't the shaders change it? It's about parallelization again. It just improves the likelihood of parallelization working, or it guarantees it actually. Because the cool thing about a shader is it's a language that's designed to make sure your code is going to be parallelizable. So in a way, it's like the main utility of a shader is doing graphics stuff on a graphics card, but it's more general than that. It's a highly parallelizable program. That's it. And because of this, and because graphics cards are getting really powerful, and because graphics cards do things better than CPUs do, sometimes people will want to run non-graphics code on a graphics card, and they'll run it in a shader. One example of that is password cracking. If you want to crack, if you want to, let's just say you want to crack a lot of passwords, or you want to try to crack somebody's password, you need to run a lot of different tests. You'll see, like, you'll just do like, does A work? No. Does B work? No. Does C work? No. And that program is highly, highly, highly parallelizable, right? So it's perfect for a graphics card. To declare a uniform in GLSL, we simply add the uniform keyword to a shader with a type and a name. From that point on, we can use the newly declared uniform in the shader. Let's see if this time we can set the color of the triangle via a uniform. Okay. So this is the fragment shader. Okay, so let's change the vertex shader to be to not have any color stuff in it. So where is our vertex shader? Yeah. Don't want this line. And vertex color, we don't want this line either. Okay, so now it just position comes in and it just writes that position out. In fact, we can actually simplify the shader with swizzling so that it goes like this, right? Because we know this is a vector 3, and then we were returning a vector 4. So we pass in the vector 3 to the vector 4 constructor, and then this is the W position. I'm pretty sure that's going to work. No, it didn't. Why not? Why didn't it work? So we didn't get an error message either. Yeah, I know what's up. This one crashed. So we need to kill this one in vertex color. There's no vertex color coming in. Yeah, it's actually the variable was missing, so just remove the line with the variable in it, which is not really good. You'd rather want to know that it's missing. So we just go vec for what color do we want? I don't know, 0.5, 0.5, 0.5, 1.0. That should be gray. Yeah, okay, we got a gray square. Okay. So yeah, we kind of cleaned up the vertex fragment shaders to what they were before. Okay, so now let's mess with the fragment shaders so that it has a uniform R color. So it's uniform vec 4 R color. Yep, that's good. We declared a uniform vec 4 R color in the fragment shader and set the fragment's color output to the contents of this uniform value. Oh yeah, we forgot to do that. R color. Contents of this. I'm a bit lost. Yeah, since uniforms are global variables, we can define them in any shader we'd like. So no need to go through the vertex shader again to get something to the fragment shader. We're not using this uniform in the vertex shader, so there's no need to define it there. If you declare a uniform that isn't used anywhere in your GLSL code, the compiler will silently remove the variable from the compiled version, which is the cause for several frustrating errors. Keep this in mind. Yeah, we kind of went through that, didn't we, earlier? The uniform is currently empty. We haven't added any data to the uniform yet, so let's try that. First, we need to find the index location of the uniform attribute in our shader. Once we have the index location of the uniform, we can update its values. Instead of passing a single color to the fragment shader, let's spice things up by gradually changing color over time. Okay, so here he gets the time value from glfw get time. I think it's a float. Yeah, it's a float. Then he gets the green value, and he modulates it between -1 and 1 using sine. It's pretty clever. And then he divides it by 2, and then adds half. And what's that about? When you do sine, you get a value between -1 and 1. But he wants the value to be between 0 and 1, because the green value needs to be between 0 and 1. So basically, he gets the time, smashes it into a format between -1 and 1, and then smashes it into a format between 0 and 1. That's all it does. Then he sets the vertex color location. He gets ID of the vertex color location GeoGet uniform location shader program R color, right? Then he uses the program shader program, and then he sets the uniform here. So these are the key lines. These two. Get the color vertex color location. Set the vertex color location. Use programming is also pretty important, but this is all about just getting a value between 0 and 1, and one that changes nicely for our pulsing effect. So let's just do that. Because it's a rendering command, I believe it should go in here inside the game loop. And he uses GL, yeah. So GL float time value equals GL FW get time. Is that right? Yep. Then green value, no, I was thinking about calling that I want. GL float green value equals sine time value. I think it's divided by 2. Yeah, plus 0.5. Right? GL in vertex color location. GL get uniform location. GL get uniform location. Shader program. Oops. Shader program R color. GL use program shader program. Oh, we already got that. And then GL uniform for F. GL uniform for F. Vertex color location. What is this actually? So, okay, so this is it's basically we're setting the 4 floats of the GL uniform 4F. So the R is going to be 0, the G is going to be green value, the B is going to be 0, and the alpha is going to be 1, because we want it to be visible. Right, cool, so that's that. Let's chat say. Hello man, what's up? How you doing? Hey Manx, doing good. How are you doing? Okay, another thing is sign is undefined. I'm pretty sure that's a math function, so we just include it in. Actually include math.h, right? And yeah, that looks good. So that's what we added. Let's see if it works. It does, and you can see it's kind of a pulsating green effect. So that's cool. Very cool. Very cool. We can speed that up by multiplying the green value. So your green value equals times equals yeah, that was stupid, wasn't it? That's not right. We're supposed to multiply time. We're supposed to multiply time, not the green value. Time value times equals 2. Is that faster? Slightly faster. Let's make it even faster. Even faster. Good, 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 good. Even faster. Good. What about a little faster? Wow! Still not fast enough. Okay, that's more like it. That's where you're gonna get the epilepsy. Alright, cool. Yeah, so that worked really well. What do? We basically set a uniform on our shader program. So shader program, and then set this uniform with this value. Later on, he talks about He just describes what we did, but I think we kind of get it. He talks about why the function names have weird names, like this. And it's because of a limit, like, why can't it just be GL uniform? Why does it have to be GL uniform and then 4F? There's also, like, GL uniform 1D, and then there's 1B, 4B, 4FV, 4I. There's loads, right? And the reason is because the C programming language can't tell the difference between different integer types, I think. Okay, now we want to know how to set the values of the uniform variables. We can set them using for rendering. If we want a color to gradually change, we can update this uniform every game we live, so it changes per frame. Otherwise, triangle would maintain a single solid color. So we want to complete revalue and update. Yeah, I think that's what we did. Because we're the best. Alright. This code is really straightforward, I guess. He's got a triangle, we got a square. Oh, he set the background as well. We should do that. Let's set the background. GL clear color. What did he set it to? 0.2, 3, 3F, right. GL color buffer bit. So now we have a gray background and it turns black. But is it fast enough? I would argue actually no, it is not. Stupid. That's much better. That's very good. Okay, cool, so we got that. Check out source code if you're stuck, but we're not stuck. As you can see, uniforms are a useful tool for setting attributes that might change in render iterations, or for interchanging data between your applications and your shaders. But what if we want to set a color for each vertex? In that case, we'd have to declare as many uniforms as we have vertices. A better solution would be to include more data in the vertex attributes, which is what we're going to do. We saw in the previous tutorial how we can fill a VBO, configure a vertex attribute pointers, and store it all in a VAO. And this time we also want to add color data to the vertex data. We're going to add color data as 3 floats to the vertices array. We assign a red, green, and blue color to each of the 4 corners of the triangle respectively. So here, it's triangle. Here's a position, and then here's a color. So this is green. This is blue. This is red. So let's go ahead and do that. I'm not gonna type it in because it's totally trivial. It's just data, really. So fuck that. Cool. I don't like it how it doesn't line up. And I don't know why it doesn't. All right, so I'll just make it line up. Yep. That's good. Cool. It is necessary to adjust the vertex shader to also receive our color value as a vertex attribute input. Note that we set the location of the color attribute to 1 with the layout specifier. Okay, so it looks like we're going to mess with the vertex shaders. Yeah, so let's change the vertex and fragment shaders. So location 0 is position. We got that. Location 1 is vec3 color. And he's calling it, he just calls it color. Right? And then we still have this out thing. Still have this out vec3 on color. Yep. So GL position equals GL position, yeah, like he did the cool sneaky stuff that we did. Our color equals color. Yep, so our color to the input color we got from the vertex data. Okay, so since we no longer use uniform the fragment's color, but now use our color as our output variable, we have to change the fragment shader as well. In vec3 our color. So this is in now, and it's vec3. Generally, it makes sense for our inputs to come before outputs. Everyone seems to do that, so let's do it as well. Color equals, oh, it needs to be a vec4. Vec4. Sometimes he adds the F, sometimes he doesn't. Like, there's an F here, there's no F here. You should always have it. Or always don't have it. I think it's better to have it. If you want it to be a float. Because we added another vertex attribute and updated the VBO's memory, we have to reconfigure the vertex attribute pointers. The updated data on the VBO's memory now looks like a bit like this. Yeah, so vertex 1, color 1. Vertex 2, color 2. Vertex 3, color 3. Knowing the current layout, we can update the vertex format with GL vertex attribute pointer. Yeah, this is a bit confusing. Basically, it's like position attributes. This is 3. I think 3 is stride. Yeah, stride is 24. 3 is a number of positions. So it's assigning the ID of 0 to the position attribute, and that's what we use here. And GL name of vertex attribute is just enabling it. So it's saying we've got 3 vectors, 3 vector 3s. They're floats. I don't know what this false is about. This is how large the whole chunk is in bytes. Why is it 6? What the fuck is it 6? I don't think it should be 6. Why is he setting it to 6? Oh, no, yeah, it's right. It's basically like, these 6 are 1 point, these 6 are another point, these 6 are another point. But start reading at 0 and only read 3. And then here it says start reading at 3 and only read 3. So it's basically like, yeah, these 6 are 1 vector. If you want to color, read these 3 and start here. I mean, sorry, if you want to position, read these 3 and start here. If you want to color, read these 3 and start here. Then this is another set of vertexes. Position starts here, read 3. Color starts here, read 3. That makes sense. Okay, so let's type that in. We've got something like this later on. But I can't remember where it is. This is shader compilation stuff. Yeah, here we go. Okay. So we've got this. 3 GL float false. This should be 6 because we got 6 per thing. And then that looks correct. So this is position attribute. And then this is color attribute. And it's just vertex attribute pointer. I don't know what that false is about. Glue index is 1 because size is 3. GL num type is float. Yep. Normalized. Aren't they normalized? I'm pretty sure they are normalized. I don't know. 6 times size of GL float GL void star 3 GL navel vertex attrib array 1. Excellent. The first few arguments of GL vertex attrib point are relatively straightforward. I think I went through it. I mean, let's just run it. Oh, no, wait. I remember one thing we need to do. These indices, we just want that. Okay, so it's all wrong. Why is it like that? So it looks like the color didn't take. The shader program is compiled okay, so no hints there. I'm assuming the error is not in the data. Oh, it is in the data. 012. Okay, so now the triangle looks correct. Yeah, it looks like the right shape, but the color is not taken. So it looks like it's a shader problem. So out vic 3 r color equals color. Out vic 3 r color. Isn't that supposed to be? Oh no, wait. Vec 1 out vec 3 r color in vec 3 color. I don't see the problem. Out vec 3. It's definitely in the shaders. Let's take a look at his shader for a second. Layout location 0 equals vec 3 position. Yeah. Layout location equals 1. In vec 3 color. Yeah, that's good. Out in vec 3 our color. If there's anyone watching, you guys should like give me some clues. But it looks like no, there is nobody watching. It's me, Banks, and Moo. And they're stumped as well. Our color. In vec 3 our color. In vec 3 our color. Oh! That's weird, he forgot a semicolon here. It's probably not intentional, is it? I don't think it's intentional, I think it was a mistake. I don't know, we can try it. Yeah, it's like compilation error. That's not right. Our color. Our color equals color. Color equals vec 4. Our color 1.0 F. Got it. Oh no, wait, don't have it. It might not be here. Maybe we're failing to pass it in. Let's check out this one. Yeah, it is here. We forgot to. Yeah, we basically the shaders look fine. Um, the problem is here we need to multiply by the size of a float. Size of GL float. Okay, let's try that again. Yeah, that worked. So a float is 4 bytes, and so it's 4 times 12. So it's basically we wanted to pass in 12 here. And because we passed in the incorrect data, it was running into some sort of OpenGL error and decided to give us a black triangle. Okay, cool. So that's basically shaders. The next part is kind of a refactor sort of thing. Yeah, he talks about why it comes out like this. It's just because it automatically interpolates between the vertex colors. Yeah, so this next part is just about refactoring everything into a shader class to make things a little bit nicer. So I'm going to do it, but I'm going to do it quite quickly because it's not really OpenGL stuff. It's a refactor. It's more C++ stuff, so I might not even explain it. I'll just run through it quite quickly. I do want to do it. So he's going to implement it all in a header file. And that header file is called shader. Shader? I think it's called shader. Are they supposed to be like uppercase or lowercase? Can we give it a lowercase name? Maybe uppercase. Because he seems to give it an uppercase. I'll rename this to main. Right. Okay, we can't. Whatever. We'll do it later. So, first things first, he just defines a structure, and we're just going to do it like this because I'm lazy. He gets the strings, fstream, stream, stream. So you can see he's going to do some input-output. He also gets some OpenGL stuff because we're going to be doing some OpenGL sort of stuff. So these are the two methods he wants to implement, and well, a constructor and a method. Does a constructor count as a method? Maybe. I don't know. Okay, so in shader, what does it do? It receives a vertex path and a fragment path, and it reads in the code from a file, and then turns those into C strings, right? And then you've got the shader code and the fragment code down here. So you know what's the funny thing is, like, if I was doing C#, how would I do it? I'd do it like this, like shader code equals vertex. It would actually be like file dot read contents, and then vertex source path, and then fragment code, and then fragment source path, and we'd be done, right? That's it. It's really trivial. But because it's C++, there's like a million lines of code, and it's all pain. It's not even done yet. Like, so this is just reading in the file. The next part is like compiling it into using the OpenGL sort of stuff we've been doing. So let's do that. I'm not going to type it because it's really boring code, and not this. I might take the second part because the second part is more OpenGL related. Okay, one. Yeah, what's up, chat? What's up, Moo? And Anus is here. Lee Sung Tak is back. Hey, Lee Sung Tak. Yeah, so he also like messes up his names. That's okay. We can kind of figure out what he's trying to do. Yeah. So next is compile the shaders. I'm actually going to type this part. To compile the shaders. The shatters. Glue in vertex fragment. Glue int. Is it? Yeah, it is GL uint, not glue int. Vertex fragment. Glint success. GL char info log 512. If you guys are wondering what this is, it's actually a string. And in C, you just upfront say how many characters your string is going to be. So we're saying this string is going to be 512 characters. So it's very static. You always know how much memory a C program is going to use, unless you use like malloc or something like that. Vertex equals create shader. GL create shader. GL vertex shader. GL shader source equals vertex 1 and vertex v shader code. No. GL compile shader. Vertex print compile errors if any. Print compile errors if any. GL shader IV. Vertex GL compile status. Add success. If not success. I'm just gonna copy this. This is error handling. Who cares, right? Is it just GL shader V? What is this? GL shader. Oh, GL get shader IV. I don't know what this stands for. Let's find out. GL get shader IV. Return a parameter from a shader object. Invoke variable. I don't know what this IV stands for. Similar for fragment shader. Yeah. So let's copy this and replace it with fragment shader stuff. So that'll be fragment GL fragment shader. GL shader source equals fragment 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 fragment. VF shader code. That looks like it's correct. Shader program. So it's a linking part. This dot program equals GL create program. GL attach shader vertex fragment. GL attach shader. This dot program vertex fragment. GL link program this program. Print linking errors if any. GL get program IV. It's the same thing. I don't want to type it out. It's too annoying. And then delete the shaders. Also pretty straightforward stuff. And then that's done. So this is what is this? It's like read the source for the vertex and fragment shaders, and then get them into files, and we get them as C strings. So we read them in as C++ strings, and then we write them out as, and then we get them as C strings because OpenGL wants C strings. C strings are basically just character arrays. And we compile the shaders and link the programs, right? That's what we did. We've done it before. It's just that we're doing it in one place instead of like smack bang in main.c++. And then use, we'll just call GL use program. This dot program, right? And there we have it. Complete a shader class. Using the shader class is fairly easy. We create a shader object once, and from that point we start using it. So, what does that mean? It means that we can actually delete a lot of code, which is great. Everyone loves deleting code, especially me. But so this, fuck yeah, this can. Oh no, before we do anything like that, we need to make these shaders as separate files. So we'll have shader.frag and shader. Let's call them vertex. Shader.frag, shader.vertex. So new file, shader.frag, and new file, shader.vertex. I don't know. And we can copy those from here because we're lazy. So this is the vertex shader. I'll just copy here, and this is the fragment shader. We just copy here, and that's a lot. Like even though we don't get syntax highlighting, it's still a lot better than before because we don't have to add in these new line characters. We don't have to add in these quotes. So we just kill this. Boom, dead. And then that's gonna stay. This window stuff's gonna stay. Compiling vertex shader, fragment shaders, linking program. Check for linking errors. Clean up. All gone. Don't want it. What else? Vertex color, location. Yeah. So if we build, it's gonna not compile. There's a few errors. It's not too many. But what do we need to do? We want to create a shader object. So we'll include shader.h. Yep, and then we will make a shader object. Probably here. Shader, and then the paths to these guys. So I forgot which one was first. What comes first? Probably vertex, right? Generally it's vertex because it's compiled first. So shader.vertex and then shader.frag. Right, and then that's gonna compile and link the shaders. And down here we want to. What's this? Go back. So shader dot program. Same thing here. Shader. Didn't work. So what went wrong? It says must write to GL position. So something went wrong with the shaders. Let's debug it. Shader.h. So we'll just assume that it reads it in. Okay. And let's just set a breakpoint here. Okay. So what's in here? shader code, shader code. That's it. Okay. Vertex code. God, C++ is fucking annoying. Vertex code. It looks like yeah, it's failing in the if we run through, we step through, success equals. Oh, okay, so that worked. Fragment, fragment, fragment. Success is 1. Why did okay? Did link fail? Ah, link failed. Okay. Fragment, 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 fragment. So linking failed, and why did it fail? Must write to GL position. We do, don't we? Linking failed. Position, color, GL position. This is weird. I mean, I actually did this yesterday, so and it worked. So I want to take a look at the code. Bullet Industries, GitHub. Shader.frag, shader.res. So shader.vertex first. Version 330 core, layout 0. In vec3 position, in vec3 color. Out vec3 R color. Void main GL position equals vec4 position 1 R color equals color. Right? Good. What about fragment? In vec3 R color, out vec4 color. Void main color equals vec4 color 1.0. It looks exactly the same. The only difference I can think of is these comments. That's the only thing I can see different here. And so if, yeah, so if that's not the error, then maybe the error is in the file reading somewhere. So let's take a look at the file reading code. So yeah, definitely, yeah, it's not working. So shader.h, vertex path, fragment path, V shader stream, path close, fragment vertex code, goes blue fragment code equals fragment shader stream. To debug, I think we should print this out. Printf. Actually, just V shader code. See what it prints out. That's interesting because I'm pretty sure I changed this. Why didn't it update? Oh, I didn't change it. Okay. Alright, never mind. Okay. So vertex looks fine. Let's take a look at shader code. Where is it? Oh, it's okay. F shader code. Yeah, that looks fine as well. So maybe it's the compile step. So vertex equals GL create shader vertex shader. Yep. GL shader source equals vertex 1 V shader code no GL compile shader vertex. Fragment equals GL create shader fragment shader. GL shader source fragment 1. Is it supposed to be 1? I think so. It's a number of strings, yeah. GL compile shader fragment. GL get shader info GL compile shader success. So this actually goes through, and then let's go one-to-one across the shader thing. GL attach shader program vertex program fragment. GL get program IV this program link status success. If not success, yeah, okay. I'm pretty stumped on this one, to be honest. What I kind of want to do is do a diff between. I want to get this and get this and do a diff. Tortoise diff. Downloads. No, I don't want tortoise SPN. I just want tortoise diff. Diff tools. Oh, awesome. Okay. Very cool. Okay, so this is the one that works. This is ours. Find the difference. It's saying there's differences when it doesn't look like there are, so it's a bit confusing actually. GL shader source fragment 1 if shader code null. GLK program IV. I mean, it looks pretty similar, doesn't it? Vertex path, fragment path. The only thing I can think of is are we passing in? Did we name these incorrectly? So this is, yeah, this is definitely fragment. This is definitely vertex. So shader.vertex and shader.fragment. And then vertex fragment. I'm pretty stumped on this one actually. And this diff is not really helping me. GL shader source. Fragment, shader program, print linking errors. It's yeah, it's the same, right? There could be an error here, but I mean, it's. We've looked at it pretty closely. Let's look at it one more time, and then I'm gonna look at the fragment shaders and the vertex shaders one more time, see if there's any difference. And if I can't see it, I'm just gonna stop and try to figure it out later, because I need to go somewhere now. Okay, shader.frag. Version 330 core. Version 330 core. In vec3 R color. In vec3 R color. Out vec4 color. I'm just gonna do. Ooh, is that it? No, that's not the problem. Out color. Okay. Void main color equals vec4 R color 1.0f. Okay. Now onto the vertex shader. Version 330 core. Layout location equals 0. In vec3 position. Yeah. Layout location equals 1 in vec3 color. Out vec3 R color. Void main gl underscore position equals vec4 position 1.0f. I don't know, maybe. R color. Right? Still no good. Still no luck. Okay, this is really not the best way to do it. But okay, so there is something wrong with okay, so there was something wrong. It's here. It's here. So let's look at that diff again. Something's wrong here. Vertex. Source path. V shader file dot open. F shader file dot open. These are comments. Compile shaders. Vertex fragment success. GL shader source. What is different here? No! Why did that even compile? Oh, fuck. Alright. GL shader source. So these are not supposed to be assigned statements. Like, that should not compile. That's where the error was. Yeah. Fucking hell, what was going on? So this is just like another one of these C++ things where it doesn't give you errors when it really should, and you just get fucked. See, I like if I don't know if I wrote that code, it would have taken me ages to figure out what was wrong. Luckily, I had like a working version I could diff it. Anyway, we got it. Just type things in incorrectly. Okay, so I'm just gonna end the stream here. Thanks guys for watching. If there is anyone watching, 2 people. Good, good. That's good enough. All right, see you guys.